So X-ray transmission. Imagine we want to talk about the simplest model we can. So we want to talk about just one material, and we're going to talk about X-rays that are coming in just all parallel to one another. So that's the simplest model we can have. X-rays coming in, and then how thick is that material is another parameter that is of interest for us. And when the X-rays are coming in, there's going to be some certain intensity of those X-rays coming in. So how many X-rays are going to be coming in? And let's assume, for instance, for now that we're talking about X-rays that have just one energy. So again, these are simplifications. On a standard X-ray system, you'll be looking at an array of energies from the highest energy, which is the keV, corresponding to the kVp of the X-ray tube, all the way down to fairly low energies, but typically usually not down to zero, because the lower energies are typically attenuated by pre-patient collimators. So, for instance, what we're talking about here, though, very simple case. X-rays are coming in. They have a single energy. This is called I0, I0. And then after those X-rays pass through this object that has a certain thickness, then the X-rays have an intensity I. So the output intensity is I, input intensity is I0. And then the transmission that we're going to talk about is how much of those X-rays make it through. So namely the fraction, the X-rays I over I0. And then we can just think about it like this. This is some arrow that's describing the intensity of the X-rays. So we have less X-rays that are making it through the patient because some of them are being absorbed within the material. And we can think about different materials and what's the properties of those different materials and compare those different materials. And we'll do so in this very simple model because it'll give us some intuition about what would happen in the human body when the human body is a combination of many materials. But the materials we can think of as basically a combination of water, air, fat, bone. Those type of materials make up the majority of the human body. So next we're going to talk about Beer's law. Do you think it has anything to do with these different arrangements of brews here? Unfortunately, it's not related to this kind of beer, but Beer's law has several names. Lambert Beer's law, and there's additional names that over time different individuals identified certain important aspects of this, and it happened first in chemistry and then moved to physics here. But we'll talk about it here. We'll just call it Beer's law for simplification now. But Beer's law basically relates what we were just talking about, that this input intensity, this I0, and then the output intensity, and then there's going to be some reduction. So this is going to be, we're going to multiply, and this is going to turn out to be a number that's less than 1. So we're going to be multiplying this I0 by some number that's less than 1, and that's going to reduce the I0 to give us the output intensity. And then that number that's going to be less than 1 is going to be related to, so we have an exponential here, and then the things that are in the power here are the linear attenuation coefficient. So this is called mu, and then the thickness of the material. So at a high level, the only thing that the attenuation or the transmission is dependent on is that attenuation coefficient and then the thickness of the material. And then this attenuation coefficient additionally depends on the material and the energy of the X-rays that are coming through. And to make life just a little bit more complicated, a lot of times people in the industry like to separate this mu out into two terms. So we're going to look at that now. But at a high level, this is all that we're dealing with, is just an exponential. So this is just going to be a calculation we do where we get a number that's between 0 and 1. And when that number is lower, that means more of the X-rays were absorbed in that material. So if we think about taking this mu and separating it into two pieces, then we can have one that's called the mass attenuation coefficient and then one that's called the density. And when we multiply those two things together, we get that same mu, that linear attenuation coefficient. But in this way, we can separate it out into two pieces. So this mass attenuation coefficient, that one is dependent on the material and the energy. And this one here, this density, is only dependent on the material. So this is the standard density that we're used to talking about for all materials, where we talk about just the mass per volume. That's the only thing we're talking about here. That's just the regular density. And if something is more dense, then it will stop X-rays at a higher rate. And that's just what this term says here. So we can look up the density. And then this one here, this term, this mass attenuation coefficient, that one is independent now of the density, and it just depends on the material and the energy that we're dealing with for the X-rays. So both of these things you can look up on the NIST website, and there's tables that have this information for elements or for materials that are commonly used in medical imaging, for instance. But to simplify matters, we've done that looking up process, and we made a little calculator for you. And I'm going to go through that calculator in just a few minutes. But at a high level, again, this is what Beer's law is telling us. And if we take this equation here, we just divide by I0 on both sides, then we'll get what we talked about before. The transmission is equal to I over I0, and then this will just be the fraction of the X-rays that make it through that material. So again, we're just writing the same thing over. All we did was move I naught or I0 over here into the denominator. So we have in the exponential of the mass attenuation coefficient times the density times the thickness. That's Beer's law. And those mass attenuation coefficients are, in general, I'm showing you here, that combined with the density, but you can find on the NIST website if you want to find fancy tables of those mass attenuation coefficients. But in general, what we look at here is as a function of energy, when we go to lower energies, that X-ray attenuation is higher. So at lower energies, the X-ray attenuation is higher. And we talked about that in other lectures as well, that if you can get enough flux through the patient, that in general you'll have more contrast at the lower energies. And that's especially true for things like bone or calcium. And then another thing we want to note here is that fat is less dense than water, and for that reason it has a lower X-ray attenuation. Then we have water, then we have muscle, and so muscle has a little bit higher X-ray attenuation than water. And then we have bone and calcium, for instance, here. And on the little tool, the little calculator that we're going to show you, you can select from some of these different options, and you can look at a few different energies as far as how are these things related as far as the X-ray attenuation and leading to the transmission through the patient. So, again, this has been the discussion on X-ray transmission and Beer's law. And then now we're going to switch over to the view of the calculator. And this is an X-ray calculator. We have several calculators at howradiologyworks.com. So if you go to the top of the page and click on the Rad Calcs button, and then the little button for X-ray attenuation, you can get to this website right here. So this website right here is what we're going to be looking at right now. And this talks about the X-ray transmission, and we have a few input parameters, and then these are the output parameters. So they're the lookup from the NIST, and then they're the calculation of that equation that we talked about, the Beer's law equation. So let's look at some given examples here. So we have tissue type. For instance, let's start with water. Most of the human body is made up of water, right? So let's start with water. That's a nice realistic thing. And let's look at thickness in terms of millimeters. So 10 centimeters. Let's look at the thickness of 10 centimeters in terms of we have X-rays that are coming in and then they're incident on 10 centimeters or 100 millimeters of water. And then the energy is 50 kiloelectron volts. So how much is going to make it through? And then this has been converted to a percentage. So we're looking at about 10% of those X-rays are going to make it through. So that would be a very skinny person or a small child, right? 10 centimeters is very small in terms of the size of a water equivalent individual. So most individuals are going to be significantly larger than this, but this just gives us a first order. Let's start thinking about how much attenuation is there going to be as the X-rays are passing through water. So 90% of those X-rays are going to be stopped and 10% are going to make it through. And then these are just, if we remember from chemistry, the density of water is just 1. And then the mass attenuation, these are the values that you can look up on the NIST website, and they're dependent on the energy and the material. So this is the mass attenuation. I don't think you need to remember these values, but more I want you to just get a feeling of, I passed through 10 centimeters of water, and now I have only 10% of my X-rays are making it through. So for a regular patient, we're going to be dealing with significantly more attenuation than that. But let's start thinking about the other parameters now. So we have water, and we're dealing with 50 keV, and 10% made it through. So what's going to happen if we switch this from 50 keV X-rays to 80 keV X-rays? Are more or less X-rays going to make it through? So if you're a practicing technologist, you'll know that when we need to have more penetration through the patient, we go to higher KEVs, namely higher kVps on the system. So if I go to higher KEV, we now have 50% more. So 15% total. We went from 10% to more than 15%. So an increase of 50% in terms of the amount of X-rays that are going to be making it through that amount of water. So that's the first thing that we're learning here. And we probably already knew this, but we're just reinforcing that as the energy is increased, we see that we have higher transmission. So as the energy is increased, higher transmission, higher penetration through the object. And we can see that that's happening because our mass attenuation coefficient is going down. So the mass attenuation coefficient, as that energy is increased, that mass attenuation is going down, but obviously the density of the water is staying the same. So now let's say we want to think about different materials rather than different energies. First, think about different materials. So if we're looking at water, and then we go, for instance, to fat, adipose tissue. We talked about that in the slides just a minute ago, but what do you think is going to happen? Am I going to have more transmission or less transmission? Right? We said that adipose is less dense than water. So if we go to adipose tissue, less dense than water, so more X-rays are going to be passing through. So adipose tissue is less dense than water. And so if we're looking at the same values, so at the 80 keV values, and we have adipose tissue, because we're less dense than water, here is, we were at a density of 1, and now we went to 0.92, and we were at 15% of the X-rays making it through. Now we're at 19% of the X-rays making it through. So 19% of those X-rays are making it through. So what we've learned again, adipose tissue, fat, is less dense than water. And what did we say about muscle in comparison with water and fat? We said muscle would have a higher attenuation, right? So if we go to muscle and we go to 80 keV, we're looking at just a slightly higher attenuation. And especially at this 80 keV, again, at lower energies, we can also see the difference as we transition. But in general, what we want to do here is just look and get a sense of the properties. And one very interesting material is lead, right? Lead is used as a material to block the X-rays coming through. And we're talking about here 10 centimeters of lead. So with respect to the units I'm showing here, I'm rounding the units so that you're not looking at many, many decimal places. But let's look at rather just 1 millimeter. So at 1 millimeter of lead, and we're talking about 50 keV, then we're going to have 0.01% transmission. So lead is very dense and has a very high mass attenuation coefficient. So both of these things lead to it having a very good stopping power. This is why it's typically used in shielding applications. And we can also look at the opposite of lead from an X-ray perspective, which would be dry air. So dry air, this is a similar mass attenuation coefficient of water, but it is not very dense at all, right? So for dry air, you're going to be getting, if you're talking about a 1 millimeter, and to the precision that we're showing here, you're going to be getting basically 100% of the X-rays passing through. What happens if we go here and we talk about 100 centimeters of air? Now we're talking about 97% transmission. And again, we're just talking about a simplified model. We're not taking into account the 1 over r squared beam divergence. We're talking about just parallel X-ray beam coming through here. So I hope you can get a sense, and I hope you can play around with this tool yourself, because I think as you play around with it yourself, do some thought experiments as to where the attenuation is coming from. Is it coming from the density of the material, or is it coming from the mass attenuation, namely the inherent X-ray stopping properties of the material? And just go through and see how different is blood if we had, how different is blood from water, how different is blood from air, and just, kind of play around and get a sense for yourself of the relationship between these different materials, and also look at that as a function of energy. So that'll tell you a lot about why we use certain types of energies for different applications. It'll tell you why, for instance, if we look up bone is going to be significantly more attenuating than water, and primarily it's going to be more attenuating not because of its density, but because of its X-ray attenuation properties. We talk about this in other lectures when we talk about the impact of the photoelectric effect, how that photoelectric effect is impacted, for instance, on high Z materials. And bone has relatively high Z materials. But in general, you can just relate this to the other learning that you've been doing. And again, at a high level, we talked about Beer's law, and Beer's law is the transmission of X-rays through a material. We just talked about very simple examples where we had X-rays coming in, those X-rays were parallel, and then some amount of those X-rays transmitted through a material of a given thickness. It's the most simple model we can think about, but it will give us some good intuition to compare the different materials, and then also to think about the energy dependence and why, for certain types of exams, why do we want to go to lower energies? If we want to look at bone imaging or iodine contrast imaging, high Z materials, for those we want to lower the energy as long as we can get the penetration, right? And we get the penetration at higher energies because the X-rays are more likely to pass through at those higher energies, right? So in general, we just, one more time, are plugging the calculator at howradiologyworks.com. Again, my name has been Brian Nett. Thanks a lot.